Here we're provided the standard reduction potentials for a number of reduction reactions, and it has to calculate the standard deltaG, or the standard Gibbs free energy for a voltaic cell made with two standard half cells, a silver half cell and a bromine half cell. And then we're going to do this for K. We're going to calculate K for a different voltaic cell. So key here is that we're told that this is a voltaic cell. So that already tells us that it's a spontaneous process and that E cell must be positive. So when I combine these two, I should combine them such that E cell is positive, standard reduction potential of the cathode minus the standard reduction potential at the anode. Okay, and then I have to make it positive. So my bromine is higher up on the table. So that's going to be my cathode. So plus 1.06 minus my silver, which is 0.80. So my E cell is going to be plus 0.26 volts. Notice if I had swapped those, like if I had tried to make my my bromine the anode, I would have wound up with a negative number, and that would not be a voltaic cell. That would be, it would not run spontaneously, which is a definition of our voltaic cell. Okay, so we've got this part, okay, and then we need the equation that connects, right? This means it's spontaneous, and spontaneity, remember we decided from chapter 19, we could determine based on the sign of deltaG. So there must be a connection between E cell and deltaG, if they can both tell us about spontaneity. That connection is that the standard deltaG equals negative NFE, standard E. So that's what we just calculated. F is Faraday's constant. You have that on your exam sheet. So 96,000. And actually, I'm going to do it in kilojoules, 96.485 kilojoules per volt mole. And then N is the number of electrons in the balanced redox reaction. And so really importantly here, you have to remind yourself that when we calculate E cell, we don't need to know how many electrons are being transferred. But when we transition over to deltaG, we do need to know. So notice that this silver gives 1 electron, but bromine is going to take 2. So to have a balanced redox reaction, I need to multiply this by 2 so that I'm transferring 2 electrons from silver over to bromine, and it's balanced. So 2 is the number of electrons in our balanced redox reaction. So I can go ahead and calculate this now. deltaG equals negative 2 times 96.485 kilojoules per mole times 0.26 volts. So that's negative 50.2 volts. Okay, so that's our standard deltaG. What does that tell us? If we were to combine, so 1 molar of bromide, right, and 1 molar of Ag plus. So like if I put those two, if I have standard half cells of those two reactions, then it is spontaneous in the forward direction, right? Which would mean that I'm going to start giving electrons from silver over to bromine. So remember our forward process, as we've written it and defined it using this, is 2Ag solids plus bromine liquid goes to 2Ag plus and 2Br minus. Okay, so we're saying that if at these standard conditions where I have 1 molar of these two aqueous components, then I'm gonna move forward and make more of them to reach equilibrium. Okay. All right, the equilibrium constant K for the voltaic cell made with standard chlorine and nitrate half cells. Okay, so we are just essentially doing the same thing, but instead of transitioning over, converting our standard E cell into deltaG, we are doing E cell over to K. That expression is K equals E to the NF E dot divided by RT. So we need N again. We're going to combine chlorine with this nitrate. So chlorine wants 2. The nitrate reaction can give 3. And so to pair these two, my lowest common denominator is 6. So I'd need to multiply this top reaction by 3 and this one by 2. So that I'd have 6 electrons given. And of course, we'd be going in the opposite direction here for a spontaneous voltaic cell. This is my oxidation reaction down here. So N is 6. Okay, 6, and then times, I'm going to keep it in joules this time, joules per volt mole, times I need E cell, which is for a voltaic cell, so it's got to be positive, plus 1.36 minus plus 0.96. Okay, so that's 0.40 volts. And then we need to divide by, and I'm gonna, since I kept this in joules, my R can be in joules as well. So that's 8.314 joules per mole Kelvin. And I'm doing this at 298 Kelvin. Okay, so this problem is probably there's some tricky conceptual parts here, but I think maybe the biggest challenge is just making sure you don't make a calculator error. Which I just did. So, answer E2. Nope. Well, give me a second. Let me model good behavior and do this punching right. There we go. So I get that K is 3.9 times 10 to the 40th. So a really big number. So when we reach equilibrium, we have like an insane amount of our Ag plus and Br minus. Like it's only those, right? We need to make a lot of this to reach equilibrium. Okay. And that makes sense. It's a voltaic cell, it's spontaneous. We're going to really, really favor those products.